Okay, hello everyone. Last class we closed the class with this on, let's see very briefly the Dalton's atomic theory. But before we start, let me give you a couple of announcements. As you might see on my on Canvas, I announced that I extended the time for homework 3. From today I decided to extend that also for homework 2 till Thursdays, okay? But remember, most of the homeworks are related to topics that I'm just reviewing with you, because you should know this based on Alex, okay? So most of the lectures are not giving this. I'm giving it because I want you to reinforce that, okay? So I'll extend the time till Thursday, but you must finish it on time on Thursday, okay? Next class also, I'm going to start with Top Hat. So be registered and be prepared for Top Hat for next class. I'm going to start with that in class questions next class. So what about the Dalton's atomic theory? Dalton's was the first approach from the macroscopic work to the atomic work. So Dalton postulated that first all matter consists of atoms, which are tiny indivisible particles of an element that cannot be created or destroyed. So he, for the first time, proposed that there were atoms as the tiny particles of the matter. The second was that the atoms of one element cannot be converted into other atoms or other elements. Nowadays, we know that that is possible with high energy atomic nuclear chemistry, but you will learn those details in jan14. Also, he proposed that atoms of an element are identical in mass and other properties and are different from atoms of other elements. So that makes sense when you see the atoms on the periodic table and the elements on the periodic table. Atoms of one element are different from atoms of other element. And finally, he proposed that compounds result from the chemical combination of a specific ratio of atoms or of different elements. So it gives us just an idea on how the reactivity and the stoichiometry work. So I won't go on so many details on how these relate to the laws we saw on last class. I don't know what happened to this one. It's not working, I think. It's not working, but well, that's okay. So I'm going to skip this, which is just a correlation with the laws we saw before. And now I will briefly show you experiments that finally determine many important things that we will use in the remaining Gen Chem class, and you will use also on your chemistry classes. So how was determined the electron, how it was determined that there were neutrons and protons, and how it was determined the charge of the electron, in that case, and the charge of the nucleus. So I'm going to show you 3 videos that you have online. You have them in Canvas available. The first is the cathode rays. So in these cathode rays, well, a source of electricity. In that time, they didn't know that electricity was made from electrons in those cases. And it has a rate like this way. Yes. So in that case, those rays, or that ray, was emitted through an evacuated tube. And the observation was that the ray bends to a magnetic field. And the ray consists of charged particles. So this is the first. So those particles from the ray has a charge. The second they saw is that the ray bends towards a positive plate. So it means it was attracted by a positive plate. So it means that the ray consists of negative particles. And then the ray is identical for any cathode. Means that these particles are found in all matter. So it means those particles belongs to the electrons. So I'm going to show you a video that explains this beautiful experiment in detail.
A cathode ray tube is the forerunner of the television tube. It is a glass tube from which most of the air has been evacuated. When the two metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to the positively charged plate, called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes the specially coated surface, the cathode ray produces a strong fluorescence, or bright light. When an electric field is applied across the cathode ray tube, the cathode ray is attracted by the plate bearing positive charges. Therefore, a cathode ray must consist of negatively charged particles. We know these negatively charged particles as electrons. A moving charged body behaves like a tiny magnet, and it can interact with an external magnetic field. The electrons are deflected by the magnetic field. As expected, when the direction of the external magnetic field is reversed, the beam of electrons is deflected in the opposite direction. In 1897, J.J. Thomson, an English physicist, determined the charge-to-mass ratio of an electron. He adjusted the electric field so that the electrostatic deflection, theta E, was the same as the magnetic deflection, theta B, and was able to calculate the charge-to-mass ratio of an electron using the following equation, where E is the applied electric field, theta is the angle of deflection, B is the applied magnetic field, and L is the distance traveled by the cathode rays. Thomson determined the charge-to-mass ratio of an electron to be negative 1.76 times 10 to the 8th coulombs per gram.
Well, in this case, as you can see, Thomson was the one who discovered the mass to charge ratio in that case. And in the next experiment, which is the Millikan's droplet experiment, you will see that Millikan used this base to determine the charge of an electron. Yes? So let me show you that.
In a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhered to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Millikan concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thomson using a cathode ray tube, Millikan was able to calculate the mass of an electron. The mass of an electron, 9.10 times 10 to the negative 28th grams, is an exceedingly small mass.
Well, in this experiment, as you can see, Millikan was able to determine both the charge of an electron and the mass of an electron. So, as you can see from the mass of an electron, this is a really tiny, small value. And that's why the mass of an electron is considered for most calculations like equals 0. It's almost nothing. And that's why the atomic mass from the elements on the periodic table is a source. So the source is just a contribution from the weight of neutrons and protons that we'll see later, not from the electrons, because the mass is so tiny for an electron. So the last one is the Rutherford experiment that determined that in the nucleus we have certain particles.
The nucleus of an atom was first discovered when a beam of positively charged particles emitted from a radioactive source was aimed at a fluorescent screen. The particles caused the fluorescent screen to glow. When a very thin sheet of gold foil was placed in the pathway of the particle beam, a few particles were deflected to the side. Occasionally, particles were deflected straight back. But nearly all particles passed right through the gold foil, as if it were not there. The scientists concluded that atoms must be mostly empty space, and that because some particles are deflected, there must be a small positively charged central mass, which they called the nucleus.
So in this beautiful experiment, Rutherford finally determined that it was a nucleus, okay? And inside that nucleus, there were the protons inside with a positive charge. So these three experiments are so important for the atomic theory, and finally discover what was inside the atom, at least the particles known until that moment. So in general terms, in the atomic theory, those experiments gave us information about the general features of an atom. So the first is that the atom is an electrical neutral spherical entity composed by positive charged particles inside the central nucleus, which are surrounded by one or more negatively charged electrons. Yes? And well, nowadays we know that we have like a cloud around the nucleus, and that cloud is made by electrons. It's spherical around that. Then we'll see certain orbits with different shape. We'll see that later. And in general, that nucleus is spherical, as I mentioned, and it contains two different particles, and those particles are protons with a positive charge and neutrons with a no charge at all. Both the protons and the neutrons contribute to the weight of the atom, not the electrons, because the electrons, despite they in theory contribute, the mass is so tiny that practically is nothing compared to the mass of the nucleus in that case. So in general, when we have this symbolism about the atomic symbol and the numbers and the mass, we have the following information. The atomic number is this seed number, and it gives us the number of protons, and the atomic number, seed, and the mass number on the top, assigned by A, is equal to the sum of the protons and the neutrons. X represents the atomic symbol. So if we go to the periodic table, now we have a periodic table here. We don't see exactly the same notation, but what we have here is seed. So seed is in the periodic table that number, 1, 2, 3, 4, 5, and so far on the top. That is seed. And seed is the number of protons. If the atom is neutral, it's easy to determine indirectly the number of electrons, because we know that a neutral atom contains exactly the same number of electrons as protons. So based on seed, we can say that, for example, hydrogen has 1 proton and 1 electron. Helium has 2 protons and 2 electrons, and so far. However, the mass number is giving us information about the weight. Yes, and that is giving us information about the sum from protons and neutrons in that case. So in this case, for example, we have an atom of carbon-12. So in this case, as you can see, carbon is here located at the periodic table. Here we have seed, which is 6. And on the top we have 12. That means that it has 6 protons and 6 neutrons. In the case of oxygen, we have oxygen 8, 16, and if we go here, we have 8 here, which is the number of protons, exactly the same as the number of electrons, and here is the atomic mass. That represents the sum of the masses from the neutrons and the protons in that case. However, we have certain variations of that, and perhaps you play with that on the homeworks. Isotopes. And in the isotopes, we have atoms with an element having exactly the same number of protons, but different number of neutrons. So that means that we have different versions of the same atom, and depending on the weight. So what we see on the periodic table, and we can tell that here, as the atomic mass. So here you can see is 1008 for hydrogen, 4003 for helium, and so far are just the averages of the whole abundances, okay, that we have for any atom. But what is true is that for many atoms, we can have 2, 3, 4, 5, or 6, or even more isotopes. So that means that for certain atom, we can have different versions, having exactly the same number of protons, but different number of neutrons. So here we have an example, and that's the case of a radioactive element. You know that the first atomic bomb was made of uranium, and here we have an example of 2 uranium isotopes. So in this case, we go here and we have uranium. So in the case of uranium-235, we have 92 protons, but we have 235 in the top. And that means that if we subtract 235 minus 92, we can get the difference, and that difference is going to give us the number of neutrons in that case. But in this case, as you can tell, in the bottom case, we have 238 uranium. And in that case, we can tell that that uranium at the bottom has more neutrons than the uranium at the top. Because if you make the difference just here, subtraction, you will see that you have more neutrons in this case than in the top case. So here we have an example of 2 different isotopes. Now let's put these on numbers, and let's see the following example. Silicon has 3 naturally occurring isotopes. We have silicon 28, 29, and 30. Yes? And if we go on the periodic table, we can go and see silicon here. Yes? If we go here and see the atomic mass of silicon, here we have 28.09. And you can see that it's not perfectly this, is not perfectly this, is not perfectly that. So what we see there is just the average, depending on the abundance of the 3. And the abundance is just the percentage of each of the isotopes in the total mix, which is what we see on the periodic table as the average. So in this case, the atomic number of silicon is 14th, as we saw from the periodic table. We can tell that, yes. So in this case, we can determine the number of protons, the number of electrons, and the number of neutrons. For silicon 28 is 14, 14, and 14. For silicon 29 is 14, 14, and 15, the neutrons, which is the difference of 29 minus 14th. And for silicon 30 is 14, 14, and finally 16. Also, we must know how to make an ion. So here, we can see how to form an ion. Yeah, in this case, we are forming a cation, which is a positively charged ion. But we can form also anions, negatively charged. But here, suppose that we want to form a cation of neon, which is relatively difficult to. But if you have a source of energy, electrons, very high energy, you can just make a collision with the surface of the atom and just deattach one of the electrons. So one of the electrons will be deattached from neon, and then you will have, instead of 10 electrons, only 9. We go here on the periodic table, you can see neon here, the atomic number is 10, and the mass number is 20. Yes? So we are deattaching one of those electrons from the 10, and now we have only 9. And because we have 1 electron less, then it will be positively charged, and it will be a cation with a positive 1. This is the base of an experiment that allows us to determine the abundance of different isotopes. just that experiment is called the mass spectrometry experiment. So let me show you a brief video of that, and then I'm going to explain to you how to calculate different isotopes and abundances. You have that also on your videos on chapter 2.
Welcome to subtopic 2.2, the mass spectrometer. The mass spectrometer is a vital instrument in many kinds of chemical analysis. But how does it work, and how do we interpret the data that we get from it? A mass spectrometer works in 5 stages. First, the sample is vaporized. Then, it is ionized. Third, it is accelerated. Fourth, it is deflected. And fifth, it is detected. The deflection stage is the heart of the mass spectrometer. When we accelerate an ion, it would like to keep moving in a straight line. This tendency of the particle to move in a straight line, its momentum, is proportional to its mass. However, in a mass spectrometer, we use electromagnets to try to deflect the ions off their path. The amount of force that the ion feels from the electromagnet is proportional to its charge. The path that the ion actually takes is a result of its mass-charge ratio. A different particle with a different mass-charge ratio will take a different path. And this is what we are actually detecting, different mass-charge ratios. So let's analyze a sample. If we vaporize it and ionize it, accelerate it, deflect it, and then detect it, we can record its mass-charge ratio. If we repeat this with more of the same sample, we will record different size fragments. Eventually, we'll know the proportions of all the different size pieces in our original sample. So how do we interpret mass spectrometer data? Let's consider rubidium for an example. Here's some mass spectrometer data from a natural sample of rubidium. It tells us that 70% of this sample of rubidium was the rubidium-85 isotope, while the rest was the rubidium-87 isotope. If we multiply the percentages times their mass and add that up, then average that over 100 atoms, we'll find the average atomic mass of rubidium. Let's try the reverse. Let's calculate the relative abundances of boron-10 and boron-11 isotopes. First, let's imagine we had 100 of these boron atoms. Let's call the number of boron-10 atoms x. Then, the number of boron-11 atoms has to be 100 minus x. We can put this together to calculate the average atomic mass, which we already know for boron if we look at the periodic table. Do a little algebra, and it tells us that x is equal to 19, which is the percentage of boron-10, and therefore boron-11 has an abundance of 81%. That's it. Thank you for watching.
Okay, so this is all the videos for today. But why is this so important? Well, because this experiment type will allow us to determine the abundance. Yes? So the mass spectrometry will tell us the abundance of each of the isotopes. So in that case, suppose that we have silver 47, which is the number of silver. You can check that on the periodic table here. And it has 2 naturally occurring isotopes, 107 and 109. From the mass spectroscopical data, we have this data. So calculate the atomic mass. So in that case, it's just simple. In this case, we just multiply the atomic mass for each of the isotopes times the percentage. And in this case, if you check, we don't have percentage in just terms here. We transform 100 into 1. And we use 0.51 instead of 51.84. And in that case, if we have that, now we have these and these, we assume the 2, and we have the atomic mass. That's the value that we'll find on the periodic table, 107.9. So let's do a couple of challenge problems for you. Do this first. There are 2 stable isotopes, chlorine 35, that weighs 34.97. And chlorine 37, which is 36.97. If the relative mass of chlorine is 35.45, that value, guys, is the value that you will see here, 35.45 on the periodic table. So knowing that, what is the abundance of each isotope? So I will give you a couple of minutes just to see how you started, and then I go on the board. After that, I have another problem more. Yes? I don't hear you. Let me go there. I didn't hear you.
I'm just kind of confused by the diagram which showed the one electron being knocked out by a steady stream of electrons and formed the cation. What's to stop that steady stream of electrons from just hitting the nucleus?
Well, it depends on the energy of the source of electron with a high energy. In that case, if you knock out an atom with a source of electrons with enough energy, you can remove 1 or 2 electrons, so it depends on. Yes? But based on experience, they know that at certain electron volts energy, you can remove just 1 electron, and you can determine that then after. Because you determine the mass to charge ratio. Yeah, so that's why you make an ionization. Because after you ionize, you will have the atom, in that case the isotope, with a different mass to charge ratio. And based on that, they will have different paths. So one will go before the other one, and based on that, you can determine how much of one you have and how much of the other you have. So that's why you need to ionize on mass spectrometry, because you need to determine the different path for different mass to charge ratio. That's the reason.
Okay, I think I'm still a little...
The thing is that, remember, you magnetize that, yes? And depending on the magnet source, it will deflect more or less depending on the charge to mass that it has, that ion. So you need to ionize first.
Okay.
If not, you won't see the difference, yes?
Yeah.
Because it depends on the magnet power that you have on the deflected area. So remember, you ionize, you accelerate, then you deflect. So it's like a curve, yeah? And you have the same source of magnetism. If you have the same source of magnetism, the difference in between the two isotopes will be the mass to charge ratio for that. That's the reason.
Okay.
We can discuss later, okay, if you want to. All right. Okay, guys, let's do that. So in this case, if you pay attention, we have two stable isotopes. So the first is that we need to imagine how to put this together and how to solve that using just a simple math equation system. So the first is that we know that x plus y is equal 1. Or we can make them x plus y is equal 100. Yes, but it's easier to work in a unit. Yes, in that case, as we saw before. So in this case, we need to define first, yeah, because we know we have only two isotopes in this case. So we know that the sum of the two isotopes will be equal to 1. Or we can make that equal to 100. It's the same. But in this case, we need to define what is going to be x and what is going to be y. Yes? So you can do whatever, but in this case, suppose that x is equal to is equal to chlorine 35, and that y is equal to chlorine 37. Let's suppose that and make this our first equation. X plus y is equal 1, and we know that x is chlorine 35 and y is chlorine 37. So your second equation must include the abundance of each, yes? So in that case, we can say that x times the abundance of chlorine 37, which is 34.97, plus y times the abundance of the other one, 36.97, is equal to the average value we have from the periodic table. In this case, the problem is giving us that directly. If you don't have it, you can go to the periodic table and find the average value from the periodic table. Look, that value is coming from here, the atomic mass of chlorine. So then it's easy in this case because what we can do is just replace X or Y depending on what you want in this case. So we can say that X is equal to 1 minus Y. And then we can include that simple equation inside that one. So in that case, we have 34.97X plus 36.97Y is equal to 35.45. And then we can include that, 34.97X. But we know that X is equal to 1 minus X, Y. So we include that here, 1 minus Y plus 36.97Y is equal to 35.45. Finally, we solve that system. And in that case, we have 34.97 minus 34.97Y plus 36.97Y is equal to 35.45. Just do some arrangements. So in this case, Y is equal to 0.24, and just by the difference, you can calculate X. So from that, you can say that for the 0.24, that is equal to 24% of chlorine 35. And for the other one, 0.76, you can say that you have 76% of chlorine 37. So that is the percentage abundance in that case. So now we have a very similar problem, and that problem is made by lithium isotopes. So in this case, we have two isotopes. So this problem is going to be solved exactly the same way as we solved before for the chlorine one. But in this case, we have two naturally occurring isotopes of lithium. As you can see here, we have lithium-6 and lithium-7. And what is the abundance of each? So in this case, as you can tell, the problem is practically the same as the previous one. The only detail is that they are not giving us the average abundance. And what is your source of information? In this case, periodic table. So you need to go on the periodic table and find lithium. And lithium is here. And that's a value you need to grab from. So 6.941. And just solve it the same way we solved the previous problem and have the percentage abundance of each. So in this case, X plus Y is equal to 1, or you can select any other letters, A plus B, depends on what you want to. So X will be equal to 1 minus Y. And then let's name X lithium-6 and Y lithium-7. And just construct the two-system equation to solve in this case. So in this case, we make the second equation. We have 6.0115 x plus 7.016 y. And finally, we place just the data from the periodic table. So I extract that data from the periodic table. You solve that, and after you solve it, I will skip the solving, okay? You can do the math at home carefully. So you will find that y is equal to 0.925. So we can tell that x is 1 minus 0.1925, which is 0.075. So from that, we have 92.5% of lithium-6 and 7.5% of lithium-7, as you can tell there. So if you pay attention on the data given from the periodic table, the atomic mass, even on the periodic table here, 6.941 is very close to the data here for lithium-6. Yes? So it's more close to that one. And it's logical because that isotope contributes with 92.5%. So it has more content of that isotope, and that's why the atomic mass that we have on the periodic table is more close to that value in that case. Any question till now? Yes. Huh? For lithium-7, so perhaps I just flip it. Just double check, okay? Perhaps I just flip it. I don't know. We need to check. So X is lithium-6. Yes. Yes, it's the inverse. Yes, it's the inverse. Thank you for that. So lithium-7, and this is lithium-6. Thank you for that. Was just writing fast. Okay. Any other question before we continue? Okay. Now let's see the periodic table. So this is the modern periodic table, what we have in hand now. As you can see, there are many features, characteristics that you need to be alert of. And here is the main group elements. And on the main group elements, you have elements on the first two columns. And you have also the elements on these last 1, 2, 3, 4, 5, and 6 columns. So those elements are the main group elements. Then after, from these main group elements, you have atoms highlighted here in yellow. And in those cases, we have the non-metals. Yeah, we'll see later in this class the properties of metals and non-metals. Yeah, from the main group elements, you have metals and non-metals. So the yellow ones are non-metals, and the blue ones are the metals. Yes? Especially, we have green ones. And green ones are atoms considered metalloids because they have like mixed properties of metals and non-metals in between. Finally, we have two important groups here, and these are what we call the transition elements. So in the transition elements, we have many metals on that place. And here, we have the inner transition metals. So as you can see here, you have like a split in here. I'm going to explain that later, okay, on this class, on the electronic distribution and how the orbitals participate on this electronic distribution. So here we have the periodic table. And from the inner transition elements, we have the lanthanides and we have the actinides in this case. So all these groups have special different properties, and we'll see many of these different properties, but particularly in this class, I'm going to highlight the properties of the main group elements. Later, in Chem 2, you will study better the transition elements and the inner transition elements in more detail. So here we have the formation of an ionic compound. So before I show you that you can make that, and you do that for the mass spectrometry. Yeah, you detach one electron and you form a cation. But chemically speaking, in a reaction in between two elements, yeah, two ions can be formed. So for example, if you have a reaction in between sodium methyl and chlorine. So the two are separate elements. They are neutral, but when you react each of them in between, in this case, sodium and chlorine, well, they just transfer electrons to each other. And this transfer of electron results in an ionic compound by transferring. One is donating electrons, and the other one is just accepting that electron. The one which is donating electron will become a cation, positively charged, and the one which is accepting the electrons is becoming an ion, negatively charged. So in this case, we have the combination of the two. And as you can see, we have here a methyl, and here we have a non-methyl, and we make a different entity in this case, which is a compound. Do you remember when we talk about compounds in the first class or in the second class, where we have compounds? But we have covalent compounds and we have ionic compounds. This is a type of an ionic compound. So an ionic compound, like sodium chloride, is made by two ions, one cation and one anion, and it's made by transferring of electrons. One is donating electrons and the other one is accepting the electrons. So it makes two ions, and the attraction is by electrostatic attraction in that case. Important features about ionic compounds is this, and we'll see this later on periodic properties also. The attraction increases as the charges increases. So in between +1 and -1, you have less attraction than in between +3 and -3. And also, when you have a smaller particle size, you have more attraction. It's more effective, the attraction in between them. So now, let's see how a compound like an ionic compound is able to be formed by electron transferring. And let's see the two streams of the periodic table. So first, we have a center column here, as you can see. But that center color is your group number 8 on the periodic table. The groups, later we'll see that, are the columns. In this case, group number 8. So here we have that on the center. This special column is made by certain elements called the noble gases. Noble gases, in general, are highly inert. They don't react with anything because they have a very specific, well, nowadays we know certain compounds, but just a few. But the thing is that they are highly stable. So they have an electronic configuration very, very stable, and they tend not to be reacting in that case. So the electronic distribution and that special way to be of the noble gases is a desire for all the elements or the remaining elements of the periodic table. So the remaining elements of the periodic table react because they try to acquire an electronic configuration similar to the group number 8, the noble gases. Yes, later we'll understand that this is called the octet rule, but we'll understand that later. So we have here on the center that, the ideal, and all the groups surrounding that will try to make that ideal. So if we go back on the reaction we saw before in between sodium and chlorine, in this case we have sodium here on the periodic table, you see? Yes, and we have chlorine here on the periodic table. So as you can see here, chlorine, yes, has 17 electrons or 17 protons, but chlorine wants one more electron because getting one more electron, it will acquire the same configuration of the noble gas, argon. Yes? So that's why it's desperate to get that. And that's why it acquires one electron and becomes chlorine negative in that case. In a different way, elements on the left from the periodic table, like the methyls and the main group methyls on the left, like sodium, in that case, pay attention on the number of electrons of sodium. 11 protons, 11 electrons. Yes? And why is able to form a cation, sodium plus? Because releasing one electron becomes the same configuration of the previous noble gas, in that case, neon. Yes, so imagine the energetic cost for chlorine and for sodium to do the following. So imagine that sodium, instead of releasing one electron, will try to trap electrons. So it needs to get 1, 2, 3, 4, 5, 6, 7 electrons to get the configuration of the next noble gas. So it's easier for sodium just to release one. Yes, energetically favorable. That's why the elements on the left of the periodic table, in this case these alkaline metals are able to form cations so easy. They release electrons easy because it's preferable just to release one electron and get the configuration of the previous noble gas. In the case of the non-metals like chlorine and the halogens here, it's easier for them to acquire one electron and acquire the configuration of the next noble gas. So that's the reason why it's easy to form, in certain cases, cations and in some certain cases, anions. Look, I want you, before you go, I want you to study yourself the naming of the compounds and the basic naming of the cations and the anions. Just the regular ones and the multi-atomic ones. I want you to be sharp for next class on that because we'll use that a lot on the stoichiometric calculation. See you guys.